So in today's lecture, we will talk about vibration or oscillatory motion, and we will discuss a specific type of vibration, which is undamped free vibration. And in the next lecture, we will discuss then the damped free vibration. Okay, so just to give you an overview of the previous lecture. So in the previous lecture, we discussed mainly about the starter crank mechanism, which include four-stroke and two-stroke engines. And then we discuss about the kinematics of starter crank mechanism. So we derive equation for the displacement, velocity, and acceleration of the piston. And then we discuss about the kinetics of starter crank mechanism. So we derive equation for the forces on the piston. So F1, F2, and PA. And then we derive equation for the forces on the crank, and finally we derive equation for the forces on the engine frame, and we also derive equation for the torque. So in today lecture, our aim is that we will talked about the vibration or oscillatory motion, and then we will discuss about the periodic and simple harmonic motion, and then we will discuss this specific type of vibration motion, which is undamped free vibration. And for this specific type of vibration, we will discuss about the how to derive equation of motion for the undamped free vibration, then how to solve the equation of motion, and then how to represent that equation of motion graphically. And finally, we will discuss some numerical examples. These are some of the reference books that we will be using for this vibration topic. So the first two books are your usual books, the one from the Gelmarium and R.C. Hibler. And these are two new books, which is the Vibration with Application by Thompson, and another one is Mechanical Vibration from S.S. Rao. These are books from which we will take different sections, and these are some figures that you can think of the application of vibration in some practical engineering application. So for example, this one is the shock absorber, which are used mainly in the automobiles, and you can also find some different applications here. Okay, so the first thing is that the study of vibration is concerned with the oscillatory motion of bodies and the forces associated with them. So all bodies possessing mass and elasticity are capable of vibration, and thus most engineering machines and structures experience vibration to some degree, and their design generally require consideration for their oscillatory behavior. So when you will be designing some structures, machines or structures, so you have to take care of the vibration also. Now there are two basic type of vibrations or classes of vibration. So one is free vibration, one is force vibration. So free vibration take place when a system oscillate under the action of forces inherent in the system itself, and when the external impressed force are absent. So the system under the free vibration will vibrate at one of its natural frequency, and we will derive detailed equation for the natural frequency of the vibrating system. And this natural frequency is the property of the dynamic system, and you can calculate the natural frequency from the mass and stiffness uh, the uh, of the system here. And then vibration that take place under the excitation of external force is called force vibration. And when the excitation is oscillatory, so the system is forced to vibrate at the excitation frequency. Now, if the frequency of excitation coincides with one of the natural frequency of a system, a condition of resonance is encountered, and the dangerously large oscillation may result. So, as you can see in this video here, this is the video of Tacoma Bridge, which was opened to traffic on July 1st, 1940, in the US, and collapsed on November 7. 1940 as a result of the aeroelastic flutter caused by wind of 42 mile per hour. So as you can see, this bridge is vibrating, and this is due to resonance here. And then you can see how the bridge is vibrating here. And finally, the bridge collapsed due to vibration. So this shows you the importance of the vibration. That it's really important to consider a vibration when you are designing your structures. Uh, and the failure of major structures such as bridges, building, or aeroplane wings is the possibility under the resonance. So thus the calculation of the natural frequency is of major importance in the study of vibration. And vibrating system are all subject to damping to some degree because energy is dissipated by friction and other resistance. uh, so if the damping is small, it has very little influence on the natural frequencies of the system, and hence the calculation for the natural frequencies are generally made on the basis of no damping. On the other hand, damping is of great importance in limiting the amplitude of oscillation at resonance. So we will discuss damping mainly in the next lecture. In this today lecture, we will mainly be concentrating on the damped free vibration. Now, another important concept in vibration is the degree of freedom of a system. So degrees of freedom is the minimum number of independent coordinates required to describe the motion of a system at any instant of time is called the degrees of freedom of the system. So thus the free particle undergoing general motion in space will have 3 degrees of freedom, and a rigid body will have 6 degrees of freedom. That is three components of the position and three angles defining its orientation. In these figures, we have in figure 1.11. So in this all three systems are single degrees of freedom system because for all these three, you only need one coordinate to fully describe the motion of these systems. So for example, the first one is slider crank mechanism, and you only need one angle theta or this x, and obviously x and theta are related to each other to fully describe the motion of this slider crank. In this spring mass system, you just need one coordinate x here to fully describe its motion. And in this torsional system, you only need one coordinate theta here. But we can also have 2 degrees of freedom systems. And more than two. So in these case, these are 2 degrees of freedom system. So the first one is two masses with two springs, and we know that each mass can move independently, and therefore you need two x1 and x2 coordinates to fully describe the motion of this system here. And similarly for this torsional system, because you have two flywheels and each of the flywheel can have its own rotation, theta 1 and theta 2. So therefore you need two coordinates here, theta 1 and theta 2. And similarly in this case here, so you have a mass which can move in this direction here. So you need one coordinate x, and then you have this pendulum which is attached to the mass, and the pendulum can have its own motion, and you can represent this by theta or x, and obviously x and y and theta can be related to each other. So just you need one coordinate here and one coordinate here, so it need two coordinates. But you can also have a continuous elastic body, such as for example if you consider a beam here. So a beam will require an infinite number of coordinates. So three per each point on the body. For example, if you consider a 3D beam problem, so each point So there can be infinite number of points along the length of the beam, and each point can have three coordinate systems. So you need infinite number of degrees of freedom for to fully describe the motion of this beam here. So we call this a continuous elastic body. Um, but however, in many cases, part of such a bodies may be assumed to be rigid, and the system may be considered to be dynamically equivalent to one having finite degrees of freedom. So, in fact, a surprisingly large number of vibration problems can be treated with a sufficient accuracy by reducing the system to one having a few degrees of freedom. Obviously, it's ideal to change the continuous system to a discrete system where you have finite degrees of freedom. So, as you can see in this case, you have this motorcycle with a rider, and you want to model this system here. So you can model this in a different way. So you can derive a very simple model from this system uh, with uh, with one mass, which is you can call is m equivalent, which will be the mass of all the component in this system here, including the rider, the wheels, and the vehicle here. And then you will have one spring, which will be the stiffness of all the structures. And then you can have a damper here. You can also try to uh, try to draw a little bit more detailed model here. So in this case, if you say that the mass of the vehicle and the mass of the rider is this one here, and then there is a separation between the mass of the rider and vehicle, and you have these shock absorbers here or studs here. So then you can say that these are the stiffness of the studs and the damping of the studs on the both sides, on the both wheels. And you have then the wheels here, so the mass of the wheels, and then you have the stiffness of the tires. So you can draw such a you can convert this a real life application to uh, some simplified mathematical models. And now we can discuss about a periodic motion. So oscillatory motion may repeat itself regularly, as in the case of a simple pendulum, or it may display a considerable irregularity, as in the case of the ground motion during the earthquake. So if the motion uh, um, is repeated after equal interval of time, which is tau, and this tau is what we call is the period of the motion, or time period, we can call it. So now the repetition time tau is called the period of oscillation, and it is reciprocal of the frequency, which is 1 over tau. And f is what we call is the frequency, which is the reciprocal of the time period. So if the motion is designated by the time function xt, so if this is uh, the function that you use for describing this motion here, so then the in any periodic motion must satisfy the relationship that xt equal to xt plus tau. So this means that this motion repeat itself after a time period t. So this means that if you are here, and then after a time period t, uh, this x is equal to xt plus delta x plus xt plus tau. So if you can call that this is, for example, if the time here is 0.2, so the time here will be x and then 0.2 plus tau. So then after one time period, this x will be exactly the same. So these both will be the same. And similarly, if you consider any other point, so for example, this point here and this point here, so these both are exactly uh, uh, the distance, the time between this point and this point is again tau. Okay, so now what about the simple harmonic motion? So in case of a simple harmonic motion, Simple harmonic motion is again a periodic motion, but this is even a simple form of periodic motion. So in simple harmonic motion, the displacement, velocity, and acceleration vary with respect to time in a way that can be described by either the sine or cosine functions. So you can represent the simple harmonic motion by either sine or cosine functions here. So simple harmonic motion is often represented as a projection on a straight line up uh, a point that is moving on a circle at a constant speed as shown in figure. So in this case, if you consider this this figure here, if you consider this and if you this is our O, the center, and this is our uh, point P. And for example, this point P is moving along this circle, and the angle here is theta, which is omega t, and omega is obviously the angular velocity here. So in this case, we know that the if this if this point P is moving along this circle, and you draw its motion here. So if you say that this is our x and this is your this is your omega t, which is your theta. So if you represent this motion here, so at time t, assume that it's here, and then now it's will be just moving this way here. So when this p will move along the line on the circle here. So then if you draw the x, so x is changing with angle here. If you are changing the angle here, so this is changing. So when the angle is 0, so this p was here, and then when the angle is 90 here, so this is the 90 degrees, and then this is 180. So then at 180 again it will be here, and at 270 again it will be here, and at 360 again it will bring come back to this point here. So in this case, simple harmonic motion is often represented as a projection on a straight line of a point that is moving on a circle at a constant speed here. So if the point P is moving on a circle, and if you project this on this line here, you will see this plot here. With the angular speed of the line OP designated by omega, the displacement x can be written as this. Okay, so x here, which is this x here. So x is just you can say that a sine omega t, and a is just the length of this line here. So OP is actually a. So you can write this equation here. And now because the motion repeat itself in 2 pi radians, so this means that the if you if you look at this thing here, so or if you just so from here to here, so from here to here, this is 2 pi radians. So this means that this motion repeat itself in 2 pi radians. Therefore, you can say that this angle theta, which is omega tau, is 2 pi because theta is equal to omega t. And now because we know that the time period is from here to here, so this means that this angle, which is omega tau, so uh, the time period here is tau. This tau is the time period, so which is the time in which the motion will repeat itself. So if you multiply the time period with omega, that is just 2 pi for this specific case, which is the 2 pi radians. So omega tau is equal to 2 pi. So from here you can calculate omega. So omega will become equal to 2 pi divided by tau. And as you know that this 1 over tau is f, so you can say that omega is equal to 2 pi f. And now omega is the frequency in the radian per second, and this f is again frequency in radian uh, in cycle per seconds, or you can also call this hertz. So now the velocity and acceleration of the harmonic motion can simply be determined by differentiating this equation for the displacement with respect to time. So if you differentiate this equation, so x dot is velocity, and velocity will become equal to omega a cos omega t, and then x double dot, which is acceleration, will become equal to minus omega square a sine omega t. And now this equation, because we know that this cos and you can also change this angle to sine here. So to make it equivalent to this equation here, so this will become equal to omega a, and you will say that it's sine omega t plus pi by 2, because we know that cos omega t is equal to sine omega t plus pi by 2. And similarly, this equation, which is again, if you change this to, so minus sine omega t is just equal to sine omega t plus pi here. So this means that the velocity and acceleration are also harmonic, because the displacement is a harmonic, because we can represent this by just sine theta or cosine theta. And then the displacement and acceleration are also sine and cosine. So we can also say that these are also harmonic functions, because we represent this by sine and cosine functions. And with the same frequency, because the frequency here is the same, but lead the displacement by pi by 2 and 2 pi radians. So as you can see here, that the displacement is a sine omega t, and velocity is again sine omega t plus plus pi by 2.